Hey guys, welcome back to another video. In this video, we're going to be talking about entropy. This is the second topic from physical chemistry. So, for this topic, I would say it's a bit intricate, it's a bit complicated if you try to make sense of everything. And the thing is, in your syllabus, it's not as in detail to understand the real meaning of entropy and comprehend the entire thing. So I'm going to try and give you a bit of detail, which might not be in your syllabus, but it's going to sort of give you a good understanding of what entropy really is and what the meaning of it is. So if we start from somewhere, let's start off with the definition first, right? So how they define entropy is it is a measure of disorderness. So let's say you have a stack of books, right? You have a stack of books in front of you and it is in an ordered state within a limited space. It is ordered. Now let's say you increase the number of books and you spread it over your bed. Has the disorder increased? Yes. Now, since the disorder has increased, the space it's occupying has increased, there are more arrangements of those books. Now, what this means is, since the disorderness has increased, its entropy has increased. And this is a common phenomena if you pay attention to, simple things in nature. Let's say there's a cube of ice over here. There's a cube of ice, and if it melts, what you're going to notice is it's going to spread out. It's not going to remain in its cubic shape. It's going to spread out and you're going to see or notice its entropy has increased. Now, why has its entropy increased? Because it is in a state of increased disorderness. Remember our definition. Entropy is a measure of disorderness, right? So if that's the case, when you're melting a block of ice, initially, it was being an ice, it had a defined structure. It had a arrangement. And that arrangement is broken off. The particles are now free to move around. Which is why its disorderness has increased. That is how we sum up entropy. Some sort of increase of disorderness. Usually, these are changes like melting. These are changes like going from a liquid to gas. Because notice, if you have a bottle of water, if you warm it up, gas evolves. And you're going to see the particles are more random. They spread out, which is why the disorderness in that case increases as well. So again, what is entropy? It is a measure of the randomness or disorder of a system. Now, another thing I'll mention. How to measure entropy? It is measured with the unit of Joule per Kelvin per mole. Joule per Kelvin per mole. Now, you may notice, where did Joule come from? Where did temperature come from? Where did mole come from? Now, the thing is, entropy is closely related to temperature. It is affected by temperature. And it is related to energy in somewhat way, right? From the units, you can already relate temperature, energy. And since it's a behavior of particles, we have mole, right? Okay, so that is a short summary of what entropy is. It is basically a measure of how random or how disordered a system is. If you have a system, meaning let's say a block of ice or a bucket of water, how disordered is it? That is its measure of entropy. Now, if you have the same thing changing state into gas, how disordered are the particles in that state? That is its measure of entropy. Okay. So, now the other thing is, when we're talking about entropy, at least in this syllabus, we're looking at it at macroscopic level in somewhat manner. we're not really going in detail into what entropy really is. Because in reality, entropy is actually the arrangement of energy within particles. When you have more particles, the arrangement of energy is greater. When you have less particles, the arrangement of energy is less. When you add temperature, you supply energy, there is greater number of arrangement of the energy within the particles. However, in AS, we are going to look at it at macroscopic level, and we're going to just take a few conditions, that is state changes, that is the how large the particles are, the compound is, and then certain things like, let's see, number of atoms, size of atoms, then what state it is in. These are the things we're going to consider to make sense of increase or decrease in entropy. Okay, so yeah, we have given you an example of melting ice, right? And the second thing that I mentioned is, when we're looking at it at macroscopic level, we talk about the movement of particles, how spread out the particles. I gave you an example of melting ice going to a state of more spreading out, right? And the other thing is, when you look at it at microscopic level, we are talking about energy, the distribution of energy. Now, there's a really good video that tries to make sense of what entropy really is, and I will link it in the description. And you will see that how the arrangement of energy affects your entropy. And it is related to the number of arrangement. Entropy is nothing but the number of arrangement. When you have more particles, it is the possibility that there can be more distribution is greater. The possibility that certain arrangements are possible is greater, which is why its entropy increases. The possible distribution increases. It is more random. When you melt an ice, the possibility that it will occupy certain position increases, which is why its entropy increases. Okay, so in microscopic level, we notice the distribution of energy within the bonds. Yep. In A2, we don't get into microscopic level. Yeah, true. In A2, we don't get into the maths of arrangements and how that affects entropy and the arrangement of energy within bonds. So actually, there is an equation, but it's not in our syllabus, which is entropy is equals to K Boltzmann constant times ln of arrangements. Now that actually gives you entropy. But in our syllabus, we'll be looking at a different formula, right? But why we're talking about this specific formula to make sense of entropy is to give you a good understanding of what entropy really means. Because entropy is actually nothing but number of arrangements in somewhat way. It is telling you how random a system can be. When the energy spreads out, which it has a tendency of, because if you notice, if you provide energy to any system, it will have a tendency to spread out, occupy more space, and have more random arrangements, which is why its entropy increases. So you notice that if you try to apply this formula, whenever there is a state change of solid to liquid to gas, its entropy is increasing because of its increased number of arrangement. So entropy is given by Boltzmann constant times ln of the arrangement. But this is not in your syllabus. Again, if you try to look at the distribution of particles, let's say I have 4 different particles over here, and this can take up a few arrangements. I've drawn 4 only, and you notice that this particle has these possible arrangement. So its entropy is related to the number of arrangement that this compound can have. The number of arrangement this compound can have. Now, notice that there is one very specific and important factor of entropy. You'll notice that since entropy is defined by Joule per Kelvin per mole, you need to understand that every compound has a specific entropy at a certain temperature. Let's say a block of ice. A block of ice will have a specific entropy at a certain temperature. If you increase that temperature, its entropy will increase. Why? The thing is, understand that entropy is nothing but the number of possible arrangements it can have, right? How disordered it can be, the state of its randomness. So if you increase the temperature of, let's say, a block of ice, what happens? The particles will vibrate even more, and they will occupy new positions, which is why its entropy increases the moment you increase its temperature. So when you're writing the value of entropy, you'll notice that per Kelvin increase of temperature, the entropy will increase as well. So your temperature directly affects your entropy, right? So if you increase your temperature, the entropy of the substance should increase. Okay, so why does temperature affect entropy? Since increase in temperature actually increases the motion of the particles and greater movement is seen of the particles. Okay, new arrangements can also be seen. As I said, it will vibrate even more, and in case of gas, it will have greater velocity. In case of liquids as well, it will have greater velocity. It can squish into other particles, and new positions, new arrangements will be unlocked. Okay, so anyways, particles also have greater velocity. Particles can get squashed and unlocking new arrangements, as I said. Right, next thing, why is the unit of entropy Joule per Kelvin per mole? Okay, since entropy is related to temperature, and increase of temperature means more energy, greater amount of kinetic energy. You should already know, probably from physics, I guess, or even chemistry, that temperature is nothing but a measure of kinetic energy. This is, I guess, in ideal gas and temperature in physics. So yeah, temperature is a measure of kinetic energy. So since temperature is related to the amount of kinetic energy, that means when you're increasing the temperature, you're increasing the kinetic energy. What does that mean? If kinetic energy is half mv square, since the mass is not changing, what is changing? The velocity is changing, right? Okay, since the velocity is changing, due to greater velocity, it's going to unlock new position, new arrangements, and therefore the entropy of the substance increases. Okay, that is why you measure entropy in terms of energy per Kelvin per mole. Because when you're increasing the temperature, it is affecting your entropy. Okay. So yeah, when you increase temperature, greater entropy. Since temperature is a measure of kinetic energy, entropy is measured in terms of Joule per Kelvin per mole. Okay, fair enough. So all of this was to give you a basic idea of what entropy is. Now, to give you a few examples again. So if you want to look at a few examples, let's say for silver and this compound ammonium sulfate, which one is supposed to have greater amount of entropy? Notice silver on one hand consists of one atom, whereas in case of ammonium sulfate, it consists of several different atoms and elements, right? And in this case, since this compound is larger, consists of greater number of atoms compared to silver, that means it is supposed to have greater entropy. Why? Because in reality, although you don't answer in this way for your syllabus, the energy within this compound has greater amount of arrangements. Since there are increased amount of bonds within this compound, the energy is allowed to have increased amount of arrangements, greater arrangements. And as a result, there is greater randomness. It is more distributed. As a result, its entropy will be larger. But how do you say it? You're going to say, since it's a larger compound, it's supposed to have a greater amount of entropy. Okay? So for this or this initial solid, which is, sort of, crystal, it has lattice structure. And in case of initial aqueous, it is dissolved in water, right? It is a solution. So what would you guess has greater amount of entropy? The one which is a solid, or the one which is soluble, is dissolved in water? The right answer is, of course, dissolved in water. Why is that the case? Because when dissolved in water, the particles itself have greater arrangements. When you dissolve something, the entropy increases. So remember, greater distribution, more randomized. So therefore, it has a greater entropy. It is more spread out, and that is a common thing when increasing entropy. Let's say considering melting, or let's say evaporation. Common examples of increase in entropy, you're going to see it is a process of spreading out, right? The particles are more spread out. Okay, so in this case, since it's dissolved, the entropy has increased. There are greater arrangements, okay? So in this case, again, the solution is supposed to have greater entropy. Okay, condensation. What is called condensation? It is turning gas into liquid. In this case, what's happening is it's a reverse process. In this case, it's going into a state where the arrangement is more systematic. There is fixed, in liquid there is no fixed, position, but it is far more restricted than being a gas. Since there is a certain amount of restriction, becoming a liquid now, the arrangement now decreases. The arrangement decreases. Less velocity, there is less distribution of energy if you try to go really in detail. But in general, you can just consider that the particles are more blocked out. It doesn't have too many positions to occupy, which is why its entropy decreases. It is in a state of less randomness, less distribution, which is why entropy will decrease. Entropy decreases. Okay, fair enough. So condensation, entropy decreases. Melting metal, of course, I've already given you the examples of state changes, liquid to gas or solid to liquid. These processes, is going to have a case of increase in entropy, more spreading out, more randomized, greater distribution, greater arrangement, which is why entropy increases. Fair enough. These were the examples of entropy. Now, to go into a few keywords. So to go into a few keywords, you're going to notice a few of them repetitively, which is one, system. What does the system describe? It is basically let's say if you have two reactants, that entire, if you're reacting it in, let's say, a beaker, that entire thing is called a system. The reactants in it becoming the products, the entire process, wherever it's happening, regardless of where it's happening, that entire thing is called the system. The change in entropy, you notice the change in entropy of the system, meaning from becoming the reactants to the products. What is the change in entropy of the system? The entire throughout the entire process. So that entire thing is called a system, from reactant to becoming a product, regardless of where it is happening. Okay, so the system is the chemical reaction itself. As I mentioned, the entire process, whatever is happening, it is considered, whatever reactants is included, whatever products there are, that entire thing is called a system. Anyways, next point, spontaneous changes. What is spontaneous change? meaning that doesn't require you to add anything to it. You don't need to do, give any sort of assistance for the reaction to take place. You don't need to introduce catalysts. You don't need to help the reaction to proceed. So it happens automatically the moment the reactants are introduced to each other. So changes that tend to continue to happen naturally are called spontaneous changes. You don't need to intervene in the reaction. Okay, so that is spontaneous change. Okay. Notice exothermic reactions, and for endothermic reactions, what usually happens is when there is some sort of exothermic reaction, energy is usually released, right? So since energy is released, the temperature usually, you'll notice, increases. I mean, always. So exothermic reactions tend to be spontaneous. If I give you an example, let's say you're dissolving a very reactive metal into water, right? It's going to, let's say, produce sodium hydroxide. It's soluble, but you'll see fire. You'll see when you touch the beaker in which you're dissolving the metal, it is warm, right? In that case, it's an exothermic process. It's increasing its entropy. However, in other cases, if you, let's say, consider endothermic processes, what could be an endothermic process? Okay, ice melting, right? Again, back to the ice. If you're melting a block of ice, you'll notice it's taking in energy from the surrounding, from the atmosphere, and it's breaking the bonds, right? It's breaking the bonds, it's breaking the arrangement, it's going into a state of greater entropy, right? Even in this case, notice that the entropy is increasing. The entropy is increasing, however, it's taking in energy, and these tend to be less spontaneous because heat is needed. Because let's say in case of melting of ice, right, you need to add heat to it so that it can melt. It can take in the energy and go through the process. However, for exothermic reactions, you don't need to give energy. You don't usually need to add energy to the system. It happens the moment the reactants are introduced to each other. However, there are, of course, certain exceptions like ammonium chloride, which if you dissolve, heat needs to be added to the system. So, of course, there are exceptions, and it's not necessary that for all exothermic reactions it needs to have an increase in entropy, or all endothermic reactions need to have increase in entropy as well. There are certain distinctions and certain exceptions as well, which is why we cannot categorize them into all increase in entropy or all decrease in entropy. We cannot categorize it just based on the fact that whether or not it's exothermic or endothermic process. Okay, so in summary, you can say most exothermic reactions, pretty much all except for a few, tend to be spontaneous. You don't need to add a heat to the system. The other thing is, all endothermic reactions are not spontaneous except for a few cases where the reaction goes from low disorder to increased disorder. Notice I mentioned that all endothermic processes are not going to be a case of increase in entropy, but in case of ice melting, which is an endothermic process, it's taking in energy and going into a state of greater distribution, greater randomness, right? Greater disorder. Okay, so in that case, of course, the entropy is increasing. And similarly, in cases where entropy is usually increasing, those tend to be somewhat spontaneous. Other than that, most endothermic processes are not spontaneous. Why? Because you need to provide external energy, or usually heat, right? Okay, so that's sort of in summary what happens with exothermic reactions, endothermic reactions, and how the entropy is related. Okay, now coming to the point of, the thing that's going to help you answering questions, especially in paper 4, the factors affecting entropy, right? The first thing I mean, the example I gave you, I guess, silver and ammonium sulfate above. Right. Silver and ammonium sulfate. So in case of that, notice that greater number of atoms will give you increase in value of entropy. Why? Greater number of atoms, greater arrangements, right? So that is why greater number of atoms will give you increased entropy. Let's say you have a room filled of 12 boys and a room filled with a single boy who's just, studying in his room. And you're going to notice that the room with 11, 12 students is going to be far more chaotic compared to the room filled with one silent boy doing his job, right? Similarly, in case of particles, you're going to notice that the moment you have greater number of atoms, it's going to have an increased entropy. Okay, fair enough. So next point, smaller atoms have larger charge density. The bonds they form are stronger. As a result, the breaking of those bonds become harder. As a result, the entropy decreases. Notice that in case of state changes, going from solid to liquid, liquid to gas, you're breaking bonds, right? You're breaking the bonds. Now, in case of, let's say, cases where you have this large ion and you have this much smaller ion, which has a greater charge density. If you remember from previous videos from chemical energetics, the one with a greater a greater radius is going to have lower charge density. But so the overall attractive power of this ion or atom has decreased compared to the smaller ion or atom, which has greater charge density, although both have the same charge, let's say +1, +1. However, in case of the smaller atom, it has greater charge density, which is why it has greater attractive force. Okay, now what happens is, when you have greater attractive force, the bond you create, let's say with another ion, or let's take an ion. So if you have a particle or compound which is negatively charged and you have formed a bond with it, if you are, really dense in charge, you're going to form a really strong bond, right? Ionic bond. And in case of cases where you have a great decrease or less amount of charge density, you're going to form a relatively weak bond with the negative charge, even though both negative charges are equal. Let's say -1 and -1. But in case of greater charge density of the positive ion, the attractive forces, the ionic bond is going to be stronger. Strong bond. Weak bond. Okay, so how does this affect entropy? Now notice that when you have a stronger bond, it's harder to break. So let's say you're dissolving this ionic compound in water. What's going to happen? This ionic compound is going to have a hard time dissolving in water. Why is that the case? Because the bonds are stronger. If the bonds are stronger, it's far more difficult to break. It's far more difficult to break. So the chances that the bonds are going to be broken down and there's going to be a state of greater disorder is less. Why? Because the bonds are being unable to be broken due to the strong forces of attraction between the ions. So the charge density affects your entropy as a result as well. If you have stronger bond, it's going to have a tough time breaking that bond. As a result, your entropy will decrease. The increase in entropy is going to be far less, right? So in those cases, entropy decreases. They tend to have less entropy compared to others. So let's say you're given two choices, one with less attractive force between the ions and one with greater attractive force between the ions. Which one will you say has greater entropy? The one with less attractive force. They are supposed to have greater entropy. Why? Bonds can be easily broken down and they can easily go into a state of greater disorderness. Okay, so this done, this done. Okay, so in case of harder objects, they have lower entropy value. Diamond has lower entropy than graphite. Okay, so when you have harder objects, again, it's a case of bond. They tend to have stronger bonds, which is why they tend to have less disorder. The arrangements are far more rigid, and as a result, the entropy is lower. So harder objects tend to have lower entropy. Okay. Right. So again, the state changes. If you consider the states, gases are going to have the highest entropy. Why? Most random, most distributed, greatest disorder. Liquid, meh, middle. Solid, least. Right? Least entropy. Okay, so notice in this example of calcium carbonate and mercury, calcium carbonate has a greater entropy than mercury. Why is that the case? Because, even though mercury is a liquid and calcium carbonate is a solid, even then, calcium carbonate is a complex compound compared to mercury, right? Which is why the number of arrangement of the energy within the compound is greater, right? The arrangement in this case is greater compared to mercury due to that reason. And of course, you're going to see certain exceptions in a lot of cases, but there are certain reasonings, and it might be out of your syllabus to be able to comprehend those exceptions. So I've just listed one such example over here, but there are a few, I guess, if I'm not wrong. So in general, entropy increases when dissolved, like when ionic compounds are dissolved in a solution, and crystallization decreases entropy because it's changing its state into a solid. So if you're crystallizing, let's say, a solution, you're changing its state into a solid, which is why its entropy is supposed to decrease. Why? Because it's going into a state of a greater arrangement. As a result, decrease in disorder and decrease in randomness. Okay, so increase in number of gas molecules increases the amount of entropy as well. So if you have a container with, let's say, 1 mole of gas, and then you have another a container of 2 mole of gas, it's supposed to have greater arrangement, greater distribution, greater randomness, so greater entropy. Okay, so in this example, calcium carbonate changing into calcium oxide and carbon dioxide, what's happening? You're changing the state from the solid to gas. The other thing that is happening is it's being broken down into simpler compounds. Okay, so even though they're turning into simple or simpler compounds, the state change is going from solid to solid, which is no state change, but the other one is solid to gas. As a result, these both changes, by the way, are going to be considered for different entropy values. So calcium oxide is going to have X entropy value, and CO2 is going to have Y entropy value. And you're going to notice calcium carbonate is going to have a different Z entropy value. Now, in this case, you will notice that this entropy, let's say, was 100 joule per Kelvin per mole. And now the entropy of this is supposed to be a bit less since it is a solid, but it is a smaller compound. So let's say it has 80 or let's say 60 joule per Kelvin per mole of entropy. And this is supposed to have the greatest amount of entropy being around, let's say, 120 joule per Kelvin per mole. So what is the change in entropy in this case? You'll notice the change in entropy in this case is in this side 100, in this side, sum of these two is going to be 180. The change in entropy is 80 joule per Kelvin per mole, right? I don't know the entropy values, of course. So I'm just making it up. But yeah, so in this case, the change in entropy would be del S would be 80 joule per Kelvin per mole. Great. So in general, as entropy increases, it is considered that the substance or whatever the particle is in a state of greater disorder, is more spread out. As a result, the energy is more distributed. As I mentioned, it is considered that the entropy overall in the universe is considered to be increasing. Therefore, the energy has a tendency of spreading out, and it wants to be in a state of greater distribution. Okay, in a state of greater disorderness, right? So, in general, whenever there is an increase in entropy, the energy is more spread out. The energy is more spread out. As a result, it is considered that greater entropy is more stable. So, turning a solid into liquid, more stable. Turning liquid into a gas, more stable. So that is, in general, the summary of entropy. And for this video, I'm going to keep it at this. And next up, we'll discuss about the calculations of entropy. Okay.